First, flexible electronics present an increasing interest for the future of microelectronics. In this context, new deposition techniques are necessary to print electronics components. This technique needs to allow localized deposition of material, high reproducibility, and possibility to transfer various materials. Some techniques have been developed, such as photolithography or roll or inject. But in each case, we can see that, for example, in the case of photolithography, it's very expensive, or for inject, the materials must be in liquid phase. So we use laser-induced forward transfer technique because it's a technique with very high adaptability. We can have a very high resolution, and it's a very fast technique. So my talk is around 4 main points. First, the lift technique, our experiment setup, and some first transfer structure. And to perform our comprehension, I use a time result shadowgraphy experiment, and I apply all my parameters for printing some structure in case of microelectronic application. So first, the lift technique. The main point is here. We have a donor substrate, which is transparent to the wavelength of our laser, and in close contact we dispose a receiver substrate. In here, on the donor substrate, we prepare our layer of material, and with a single pulse we can transfer a pixel between donor substrate to a receiver substrate. We can, with this technique, we can print a very wide range of material. So the motivation of this today is in case of microelectronic application, so to print passive components, 2D and 3D connection, or switches. We need to know ejection mechanism, transfer, and we can perform our technique for transfer on flexible substrate. We need high resolution and high conductivity because it's for microelectronics application. We try with a very large choice of material, and the previous results with paste is very promising. So we print with high resolution, and we can control very well transfer structures. So we need to understand the ejection mechanism. Our material for these studies, it's paste. We buy at Arima Chemical Corporation, and the important point is the very high viscosity of this material. It's very important compared to air. We use two different types of receiver substrate. First, silicon oxide for reference measurement, for conductivity or structure of our layer, and in case of microelectronic application, we use a Kapton substrate because it's very flexible and the mechanical properties are very stable. We print first some pixel, and we see different kind of transfer. First, we observe droplet, or we can observe square, but sometimes we can observe very strange structure. So it's the same material with the same condition, but we observe very different structure. So we need to understand condition and mechanism of transfer. We made a time-resolved shadowgraphy experiment for that. We observe this kind of picture. So here, in this part, you have the donor substrate with our layer of material. Here, it's a receiver substrate. So this one, the distance between both is around 800 microns. And here you can see the ejection at different time after irradiation of laser. So in the first time, we can see anything, but after 5 microseconds, we can see something is ejected here, and with increased time, we can see the droplet here with a little filament, and after 200 microseconds, we deposit something. So if we see which kind of structure we print, it's droplet with no debris and no splashes all around, and no coherent effect at the top. If we try to understand the mechanism, it's due to the laser irradiation here, because the observant at this long wavelength. We observe a bubble formation here with a very high pressure and very high temperature. When this bubble is expanded, we observe here our bubble and a filament, and the filament will shrink with time and with expansion of this bubble. So it means that it's the same thing as a regular instability. If we compare, for example, two different fluents, we can see the same mechanism, but we can inject with high fluents more material here, and the filaments are shrink very quickly. But if we see here our deposition, we see the same kind of pixel than before, like a droplet, well defined and without phase shift. If we compare the speed of ejection here, we can see that the influence plays an important role on the speed of ejection. In the red part, you have a high fluence, and in blue, the low fluence. But in each case, we can say that the speed is inferior than 550 meters per second. If we compare with the time, so in this case it's the same picture, but if we increase the time before the irradiation, we can see the same mechanism of ejection. But if we see here the deposit, we can see this kind of structure. They seem the next picture with a very strange structure, and if we increase the time, we change a lot our transfer. So the time is an important factor for determine our structure printed. We observe that if we increase time, we increase the ejection speed. If we compare with high fluence, we observe exactly the same thing, just here you see the filament, and in this case, at 1 hour and 3 hours after, we observe that the filament disappears very quickly. If we compare here the speed, so in red with the high fluence and in blue with low fluence, we can see that the speed is exactly the same after 1 hour and 3 hours. So now we print this kind of pixel, and we apply this characteristic for transfer droplet and line for our application. So we can print very well-defined droplet with a very smooth profile and well-defined. With this droplet, we can print a matrix to perform repeatability. We can see that it's very reproducible and with a well-defined deposit. If we decrease the distance between two droplets, we can print line. Line, we can see there is no splashes, no debris, and very smooth profile. And if we apply this kind of transfer, we can print some component for microelectronics. First, to transfer passive component, we need to characterize our deposit. So for that, we use first a process of annealing to melt nanoparticles and evaporate the solvent of our paste. After, we try to nanoindentation measurement to determine the Young modulus and hardness of our paste. We can see that it's less than bulk for Young modulus and hardness, but it's enough for our application. If we try to AFM measurement, we can see here very low roughness, and it's the same that the nanoparticle size, so it's a good result. And to finish, we make an electrical characterization with the Van der Poel method, and we determine that the resistivity is around 6 microns per centimeter, so it's very with the very high conductivity of our material, it's not really adapted for printing this kind of component. But in case of inductance, we have the same problem, but we can print. You can see here just single inductance. But for example, in case of capacitor, we can print all by lift the layer. So here you see the pixel of paste, and on top here you can see the second part. So it's PVP for the electric layer and silver for conductive contact. You have here the characteristic of two layers, and we measure 4 picofarad, so it's very small capacitor, but it works. Finally, we can print some membrane switches. So here you have the bottom layer of switches. Here you have the structure on the top layer switches. And when we push here to allow a contact between button and electrode, we can measure the contact resistance, and we can see that the contact resistance is very stable for a lot of cycles, and it decreases when we increase the actuation force. So to conclude my talk today, we perform with a time-resolved shadowgraph experiment our knowledge of ejection mechanism. I show you the influence of solvent evaporation and how to control pixel morphology. We can print lift, droplet, and line, and with high resolution, no coherent effect, good replicability, and close to bulk resistivity. And in case of microelectronic application, I show you that it's possible to print passive components and functional membrane switches. I would like to thank all my partners and thank you for your attention.
Do we have a question or two for this talk?
Do you know practically what the working window is, the time window, where you can print nice structures with your paste?
In fact, I print nice structure just after I prepare my donor substrate, because if I wait too long, for example, for 1 or 2 hours or 3 hours, the structure which is transferred, it's strange. We don't control exactly which kind of structure we can transfer.
Thanks. Is it right to think that at a very early time, that is when you have the most solvent present?
Excuse me.
Your answer to that question was that you use your substrate as early as possible. Is that when it has the highest solvent content?
Yeah, in fact, paste is charged with 85% of nanoparticles, so we have solvent, but not very important quantity. And I think during time, so after 1 hour, 2 hours, some solvents are evaporating, so the texture, the viscosity of paste and the structure of paste, it's not exactly the same, and I think it's for that we can see this kind of structure.
Okay, if there's no further questions, please wait here for a moment, because at the end of the first session, the winners of the poster prizes for session V were read out. Do you know this?
I'm not sure I understand.
Okay. Well, at the end of the first session, 3 young people were asked to come and receive certificates and prizes for having presented prize-winning posters.
Yeah.
And have you received your prize?
Yeah.
Okay. Congratulations again.